Okay, so let's start. Good morning. Welcome to this fourth lecture in the series. We started off talking about in lecture 1 and 2, there was more general multi-scale problems, first of more general later, and then the heterogeneous multi-scale method. So this time we'll focus on wave propagation and more on the algorithmic side, the fast algorithms for doing that. And we'll look at seismics and optimal transport techniques applied to that in the final lecture. We already touched upon wave propagation in the second lecture, and it was multiscale of a different type. It depended on strong variation and oscillations in the material, or rather the variable coefficients in the partial differential equation. Here we will think of more smoother coefficients, and the highly oscillatory part comes from high frequencies. That is the boundary condition and the initial condition in the problem. And that's sort of a more common thing, problem for wave propagation. So the challenge now is high frequencies in the setting, and that's what causes a lot of problems. So we'll first talk in general about the setup. We'll then go into the algorithmic part, and there are two types of problems we look at. One is the integral formulation, and there we'll rely upon the fast multipole method structure to do something. And the other is when we have a differential equation formulation, both in frequency domains. We think Helmholtz equation or similar equations for elasticity or electromagnetic waves. There the problem is preconditioning to that's sort of the challenging thing. And then we look at the techniques that we have studied and see if one could do something better. So we're looking at the other side, saturation result or low rank estimates to what we have done, the other side, and then there would be the agenda. So we're looking at problems that could be described by wave equation, acoustic, elastic, electromagnetic. And if we have, or most of these problems are of the type that the domain versus the wavelength is quite large. So the wavelength for your cell phones is of the centimeters. The distance to the base stations are in hundreds or meters or kilometers, and therefore it's a challenge if you discretize them as always. So if you go back to the thing we talked about before, in order if you don't have anything more, you need at least 2 points per wavelength, and here you would need even more in usual to get certain accuracy. And that is a challenge. So one possibility is then to change the problem, to do asymptotic techniques. Here it turns out it's not so easy. Geometrical optics, geometric theory, diffraction, the adding on Gaussian beams, etc. It's a lot of special cases if you do a general geometry. And you run into difficulties not only with the classic analytic problems of caustics, etc., but just complexity if you have scattering around all these different corners in a city, for example. So usually there people would prefer as far as possible to use the wave equation formulation. You can do a little bit there. You can reduce the dimension that you have. Instead of 3D plus time, go down to 3D by itself by looking at in the frequency domain. Very often that is an approach where it's dual. If you're broadband signals, of course, you need many of those. And if you then furthermore have constant coefficients, or at least piecewise constants involved, then you can rewrite it in potential theory as an integral equation, and then reduce the dimension to only solve in the manifold. What we will focus on here is the fast algebraic solver. Once you discretize and you have your algebraic problem, and there we would sort of play both with the algebraic techniques and the analytic technique or analytic formulation, knowing from where the problem comes from, and that turns out to be essential in the structure. So here we are. So we, of course, have the problem, and we'll describe it in terms of Helmholtz equation all through the thing. We have some applications of the other things. You do some discretization either on the differential equation level or the integral equation level and end up with an algebraic equation. These are linear problems. So these are large, huge linear system of equations that comes in over here. Well, this is, of course, also important if you have higher accuracy, you need fewer points per wavelength, etc. So, but that's not the focus of this lecture. There was more the first two. So we are sitting over here. And we have two cases that both have their challenges. So one thing, if we do integral formulation, so we have a little bit lower dimension, then the matrices are dense. So that's the challenge. We will, in both cases, they are huge, so we need to do iterative solvers. So meaning that if we have the matrix sitting over here, we need to multiply several times vectors with this particular matrix in the different kinds of approximation that we have. Okay, so there the challenge is to reduce the matrix vector multiply cost. And that will be done then by some form of fast multiple method. In the other case, we have PDE formulation. It's sparse. You don't want to mess with that this operator, because then it becomes denser and costly. So the challenge there is that the conditioning is not so good. So inside here, you would need enormous number of iterations. You need to do preconditioning. And of course, the precondition is the inverse, so that is a little bit like the dense equation that we had, the inverse of a differential equation. So that's the scenario. We have two different paths to go. One is the integral formulation, and the other. If we have a similar problem, it wouldn't be the Helmholtz equation, then there are a number of techniques that scale perfectly in this way, the conjugate gradient, if it's symmetric, if you have a multigrid, etc., and the fast multiple method for these problems. And you have the integral, the primitive function, the Green's function, has a nice structure, particularly a nice structure at infinity. It's regular there. The Helmholtz equation doesn't have that, and that's the challenge here. So you have, it's hard to approximate the far field in a good way, in a compressed way. Here, of course, it's Poisson series tells you what goes on at infinity very accurately with a few terms. So that's sort of the challenge. And we'll start off here, and we're thinking about the frequency domain. We get a problem here where the Green's function is sitting, multiplying the unknown, the potential that we are looking for, and the choice of potential, the choice of formulation could be either first or second kind. We can think second kind here because we are not focusing on, which is then more better condition, so we don't need to think about precondition. There is also a preconditioning problem here otherwise, but let's think about that. So if you discretize that, you would essentially get the leading part where the Green's function is sitting as the matrix. It depends on a little bit the quadrature, but usually you can do that in a way that most of the features of the Green's function comes over here. So this would be the A that we are looking at. So let's repeat a little bit what the fast multiple method is. The Griegard-Rockling algorithm that has been very much appreciated in this kind of thing, regarded as one of the major algorithms over there. It started, of course, a little bit before that, and I'll come back to that, what Rockling did earlier, and other people have done similar things. So with this could be quadrature point in the integral equation that we have over here. But it may be easier to think about it in this terms, that you have a galaxy of stars and you are interested in evolving the dynamics of this. So you need to know, using Newtonian law, the forces from all other stars to each star over here. And you need to sum that up. So you have n stars, and for each one you have n forces. It's an n square problem to deal with. So you can express it in this way, where the force depends on the masses of where you are and the masses of all the other stars and the distances and relations to all the other stars. So that's the original problem. So what they did, Green, Gardner, Rockland here, was to represent this in a way that when you did the summation, you separate it out in different parts where you would see that away from a certain group of stars, you could do a simplification, as we do when we calculate gravity from the moon to see the tidal waves. We just do the center of mass, the center of gravity over the moon and the distance vector to the moon, and that's it. That's a very high accurate thing, and you can correct with moments. We'll come back to it. And that's what they did. So you take this form, you expand it around the center of gravity and rewrite it there, and then you get a small term where the difference between the center of gravity and stars over here divided by the difference to the star where you are. So this would be a small term. You throw out that, and then you get an approximation which is precisely just using center of gravity instead of doing that. And this is then a monopole. This is a pole over here, approximation, and that would, if you're far apart, this would become accurate enough. One thing you could see is that the calculation over here, the calculation of the center of mass and the masses, only depends on the stars within this small area, the little box, the J's. And the calculation of the distance to the center of gravity only depends, or once that is fixed, only depends on the different star where you are. I in this case. So you have a separate expression in terms of function of xi's and the function of xj's in this case. And this separate representation is, of course, analogous to this representation. You can write this in this term. And if you have a separable representation, either in terms of vectors for a matrix, or in this case, continuous-wise, then it means that this particular piece, which means connection between the local stars that we were using the center of gravity of and the other stars, would be part of these interaction matrices. Here you have the forces, here you have the masses, and here embedded is the distances. And that can then be written in this particular form, and that's just an outer product. So it's a rank 1 thing. So it's very fast to multiply with this matrix. It's just one vector, and then you take the other vector doing that. So this is order n, even if you have an n vector, instead of n square if you would do that fully. So this, you have 3 formulations: the multipole, the separated approximation, where you write it in this form, and then you have a thin SVD, and it's very thin. It's just one vector in this case. So we will play with all these 3 and see when to use one or the other. Now, of course, you can get a better accuracy by including more terms in the small variable over here, or small vector valued variable over there. If you do that, you get multipole expansion, so you get this, and that's the name that they used to call this in this way. What does it mean on this side here? It means that instead of just a product of A depending on one group and B depending on the other, you have a sum of products. So this is what we call a separated approximation, and one can do that as accurate. And on the SVD side, a representation of a matrix, it just means that instead of one vector, you have a few vectors here, and you have a singular value decomposition type matrices, which is all, again, fast, depending on how many terms you have there or how many terms you have there. So these are the settings where it's used. Then, on top of that, you have a strategy for using these compressed things. So we take the simplistic case over here where you have, let's say, n stars. You group them in square root of n groups with square root of n stars in each of those. And then you can see that nearby a star, then you cannot use this approximation. You have to do it directly. So you have, for each star, you have to do this, n. But nearby, you only have a finite number of square root of n. So you have n times square root of n, this amount of cost At the far field, you have square root of n boxes, but you only need a finite number of operations for each of these stupid boxes. So you get this gain from n squared to 3/3. Now, if you do that hierarchically, so that the nearby neighborhood is very small, and then the far ones and the even further one, you have larger boxes, you have these layers if you go from one finite number of stars to a finite number of boxes, log n. Now you can gain even on that. So you can go from log n to a constant if you do this hierarchically construction-wise also. So instead of doing the multipole expansion or center of gravity for a box with many, many stars, you do it with very few stars, and then you use the multipole expansion or the center of gravity there when you go to next level of larger boxes, and they use infinite of them next level, and then you get a geometric series, so you don't get the log n in this. And then once you have calculated that, when you do evaluate the forces, you also start with larger forces. So here you have a Poisson series, you can say, where you expand on the far field, and here you have Taylor expansions when you compress back. So that's the overall strategy, and that worked very well. Now, it doesn't work well if you use Helmholtz equation here. And what it turns out is that you need, in the multipole expansion, you need enormous amount of terms in order to resolve the features over here. The same thing if you have a SVD, the very few singular values that you had in the elliptic case becomes an enormous number in these in particular. So it is not working. And actually interesting, because this is the way this problem with Helmholtz was the way that Rocklin started with. He worked at Exxon, he was student at Rice, and this was his thesis. And it turned out to be sort of a bit iffy. This is what he did. But if you over-resolve the problem, so if you have an enormous number of unknowns per wavelength, then it's essentially on the algebraic side elliptic. And then you could see that it worked, but it didn't work so well. So it was the algorithm took off when they applied it on elliptic problem together with his student Greengard then, at that time. Then once I came back and we worked a little bit on this the way it was, and tried to in the far field do Hankel functions to do that, and it was never worked so well. So the way to do this, we believe, was when we started working with Lexing Ying on this problem, was not only do you need to divide it up in far and near field, furthermore, the far field has to be a little bit further away, but if you divide the far field up in conical domains or sections or sectors, so you have a directional then you can get this compression. So the thing is, of course, that in different ways, analytically, you can approximate the wave propagation in constant coefficients, which we are talking about here, in different ways along that. That's the ideas of Gaussian beams, the ideas of paraxial approximation, etc. And the question is, can one turn this into an algorithm, and can one turn this into understanding why it works? So we proved a theorem there of the simple type that you have the Green's function can be represented in this way as a product of function only depending on particles or points or quadrature points in one domain multiplied with the ones in another, and you do a sum of that is over here. So that is that could be done uniformly in these domains. So either you could think about that you have domains and you have different omega, or you could think about that you fixed omega being one, the frequency, and then you have a different variety of domains of different sizes, easily to scale. But the important thing is that there is a separated approximation, and you get this estimate where this guy, the number of terms, does not depend on where you are in these domains. One is infinite, and in omega in this case, or the scaling of the domain. So that's possible to do. This also depends rather weakly on the error that you have. It's of log term, log form. But the important thing is that you uniformly can do this approximation. In order to prove that, what we did was to take all the individual pieces in the Green's function, the exponentials, the Euclidean norm distance, 1 over the Euclidean norm distance, and each one of them show that you can have this separable uniform approximation in a finite number of terms, and then you combine them together, what it is. And the type of approach doing this, it's rather lengthy, but it's very sort of simplistic in the sense that you only need calculus, a little bit of analytic functions. So the idea is you do first in all of these cases, you do some transformations, you get it in a form where it's reasonable to do a power expansion of some sort, where then you see each individual term is of this type. And then you have to show that these terms do decay in a certain way. So first of all, that you get convergence rapid enough so it's uniform, and also you need a finite number of terms that depend very weakly on the error estimate in this case. So you need to go through. So this was one type of terms, but it becomes many of the steps there are just cumbersome, but that's it. But anyway, in the end, you can show that that's possible, and that's sort of the underlying mechanism for this to work. That if you do this decomposition, then in different parts, then it is fine. So that was analytic way of deriving, and that's also important. Now, if you follow the proof, which is constructive, so in principle you could do that, it's a big mess. Yes?
So that's a way when you can restore at least n log n operations, but you have constants floating around, and the constants may depend on epsilon.
The constants depend on epsilon, and
that's a number of, that's a rank.
Yes, yeah. So that's right. If you follow the details of the proof there, it depends logarithmically on epsilon in this case. But still, they could be large because they're constant times the log in this case, so it's hard to control. Actually, there are similar ways of doing this. This is more sort of direct, and the proof applies to proof structure. I would say apply also to 2D. This was 3D as I wrote it. There are people in the applied physics community that have done this by using special functions, and sometimes you don't get the domains that we had exactly, but otherwise more precise estimate than what we did with polynomial things. So there exist similar things over there. They base it then on Bessel and Hankel function expansions, which is asymptotic one in this case. But so one thing here is that this is costly. So once you know where to compress, then we go into an algebraic feature and do that with singular value decomposition. So that is important over here. So that turns out to be much more efficient to leave that. Now, do we all need just sort of a proof to do that? No, it's very important to know where to look. If you do this in sort of a data science point of view and look at the full matrix, then you have to find out which are the domain in the matrix, which is a mess in 3D, depending on how the meshing is and all of these. So you have scattered values. It's not like one compact part in the domain, XY domain is in the matrix. It sits everywhere. So this is an NP-hard problem to do that. So you can't do that data science-wise directly. You have to know what to do. But once you know that, then you can go in and use singular value, which is not NP-hard, and it's algebraic in this case. And we do that random-wise because there are still large problems in this case. So that is a structure. And then there's one thing that is different from the other is that in order to get n log n, you need to use the fact that we are doing integral equation. And we are not doing galaxies. That is, you need to know that the points lie on a codimension 1 manifold in this case. That is part for the n log n. Otherwise, it becomes algebraic again. So, of course, it's a harder problem than doing this. OK, so there we are. So in doing this, once we have selected, so it doesn't look like that in the matrix, it's sitting everywhere, but if you take this into account, you would like to do that in the thin SVD, and then we take a random number of of rows and columns, do a singular value decomposition, and write it in this way. So that's done with a randomized, these are QR operations in there. So then you get an expansion in terms where these guys would be sort of the multipole coefficient or the singular values that comes in here, and here you have the vectors sitting. There's a little bit different. Instead of representing with multipoles, you could then represent the impact of all these points by 1 point, and multipoles. You could also say that I represent them by a few points and then adjust the masses in doing that. That's just technique, and that's the way it was done here. In order to do it effectively, you need to build sort of the far field coefficients, or the multipole expansion, based on smaller domains, and then collect it in a larger domain in doing that. And that can be done also here. So once you have on these, what does it say here? B prime or star or whatever, I don't see there, and that expansion is valid in a wedge like that, or a conical region in 3D. And then if you have the other guys, the other 4 guys here, or 8 in 3D, you use them in order to get the expansion in B. It turns out that all of them are wide and near, because of the scaling. This is, if this is a size is r, this is r squared, and this is 1 over r in the angle. So when you come to a bigger one here, it's further away and it's smaller angle. So therefore, you can use all of them to build the expansion in this guy. So you can follow the recipe in otherwise, but of course you have to do this for all angles. That is n log n, then it is just to sum up all the different pieces. In this case. So first of all, you have a level of boxes, because if you have larger boxes, then you have to be very far away, or in this case, you cannot go to order 1 size in these thing. You have to stop at the square root of n distance in doing that. So these are the number of boxes that are involved. And then you see how many of these boxes are intersecting the manifold where you solve that. So therefore, you have this number of boxes over here. Then you say, how many wedges do these boxes have? And that you check in this 3D thing, how many these are in this case. And then you have a finite number of operations, because you build them up from the bottom to do these things. And you add all these things up, and it becomes n log n. So this is, but here is a crucial part, of course, that you do this in n. So if we look at a 2D profile over here, you see that you only need the refined boxes around here, and of course you don't need them in the distance. This is typical challenge with the stealth technology. So the test cases there are in the literature are usually fighter jets or robots and things like that, and to run that. And you see, if you go through the numbers over here, that both the number of the times to build this system and the numbers used in the iteration with the QMRS scale essentially linearly in the number of unknowns. And here, that is in here, of course, depends on the wavelength along the manifold in this case. So that works pretty well in doing this. So that was the integral equation case. Yes?
One more question.
So yeah, that's a part of it. So.
Your observation on asymptotic masses is, of course, relevant about the difficulties with the possible singularities and angles and so on. But on integral equations, you should find them back in some sense hidden. Don't you find them? Because an angle or even worse, a cusp or something like that should create some difficulty intrinsically.
In principle, that when you aggregate it will do that. I mean, here we're just looking at the Green's function as it is here, and doing the compression on that level. Now, when it comes to the solutions, then it depends very much how these points, that is, how these Green's functions add up in the solution, as you say. And there it depends very much on how that looks like. Not so much for the algebraic side over here, but for the accuracy it does. That is, how do you do the quadrature? So here, hidden in this, I would say, would be that you should think of a smooth manifold, because otherwise you get accuracy problem. Here we only thought about the accuracy in solving the linear equation. Of course, the real thing is the accuracy of solving the differential equation.
I was worried about the jet.
And there, yes. The sharp edges over here requires a lot of work on the quadrature. If you do boundary elements, or if you do Nystrom method, that is there. But as I said, I leave that out of this discussion here. I'll look at once it's a matrix problem, then it's only point by point, and we don't need to. But how they add up is, of course, that's what gives rise to the general theory of diffraction, which tries to compensate that and all. So that's true. So there are problems for the full setting where that needs to be taken into account. Yeah. Okay, so now we switch. This was the first part. Now we go to the second part here. We have the PDE. The difficulty is there that once we put it in there, we require it to be better conditioned. And in order to be conditioned, you need to do a preconditioner. That is, essentially, you need to, as well as you can do, multiply with the inverse of A, and the inverse of A is, of course, a solution operator. The Green's function comes in there again. But if you do that, of course, it's too costly if you have a true inverse, so you need to cheat. And that's what we do. And if you do the regular cheating, that is done with the like using incomplete LU defactorization or the multigrid. What happens is that you get another approximation of the problem, and you get another dispersion error. And these are sharp signals over long distances, meaning that if you have a little bit error in the dispersion, if you go further out, you get an over 1 error, because you saw the oscillatory kernel if you shift that a little bit. So therefore it doesn't work, and there are even papers by Martin Gunder and company about the difficulty in doing these things. So the observation over here, sometimes it's slow here, is that you should try to start off with the approximation you have and do something about that. So this is the idea, because of the difficulty with the dispersion over here. So we'll try to do something there, and the compression, as we had in the earlier part with thin SVD, will play a role also here. So let's say we have the domain here, and it turns out to be open, important that the Dirichlet boundary condition, for example, or Neumann or whatever over here, but that you have an open boundary here, so we don't have reflection. I'll come back to that in the later. And then the ideal thing would be to do Gaussian elimination, let's say. So you eliminate line by line by line and produce the inverse that way. So you do this, and we call it there sweeping, because we will then do something to the Gaussian elimination. Because in 3D you can do the same thing, but you go well, represented in 2D also here all the way. But in 3D you can do that also, of course. But then it's sheet by sheet, layer by layer in the Gaussian elimination. So if you do that, you have the original matrix, which is a sparse matrix, and write it, let's say, with a 5-point formula. So even these blocks are extremely sparse. The B's are just diagonal, and the A's are tridiagonal. But when you do the Gaussian elimination piece by piece here, LU or LDL representation, then you get fill-in. Not over here, but you get fill-in in these blocks, and that gives that the matrix will not be, the work will not be order n. It will be n depending on the dimension, n square, for example, in 3D. So the idea, and that in the end, these would be filled up, and also the L would be blocks would be filled up. So then you lose. And of course, you would do. You cannot expect that you can use the Gaussian elimination as a way. So the observation here is that the corner block over here in the full setup that comes, this is a process here, and that connects all the values once you have done the elimination. That corresponds then to the half-space Green's function. If you write the full Green's function out here. So this interaction that is sitting over here in the decomposition that connects all the unknown ones, these are eliminated and they are put into these places. We went from here to there. This guy is an approximation of the half-space Green's function. And this guy is compressible. In the same way as the Green's function was in the further way, in the earlier setting. You can also see that one point over here, if you take all the other points, they would be in this conical domain that we had over there. So it compresses in the same way. And you can write a theorem there, because this is along a line here in 2D surface. You can do a little bit better, so you can let the domain go very close together and in this way. So that is possible. So the idea is to start off with the Gaussian elimination and then compress to a form that is a thin SVD again. So that's possible. And here you can let this X and Y domain come arbitrarily close in the estimate here and still have a finite number, also depending on the log of the error estimate and the finite number of those, meaning finite number of singular vector that are important. And you could see that, we'll see why later, that if you do Dirichlet boundary condition, you have these blocks in a matrix. This is a 1D problem. So it's 2D is the matrix looks like the domain. And there you have large number of singular values different from 0. And if you use these open or PML in this case, you have lower in there. So you need that part in order for it to be, it need to be a half-space Green's function. Otherwise the connectivity is not there. And that's also then proved by the same techniques as in the earlier setting. Now, it is important that you cannot do the same way. In the integral equation, we were given the Green's function, and then we could compress it. And work with it when we did the multiplication. Here, we are not given the Green's function. That is calculated on the fly when you do sort of the Gaussian elimination. And you cannot then compute them first and get all these unknowns, fill in, and then compress, because then you have lost the game, because the cost is to do that. So you have to stay within the whole work in order to produce these. You have to stay with thin SVDs. Fortunately, these Leipzig people have developed an algebra to deal with that. So if you're given matrices on the form as thin SVDs, then you can put it into their system, more or less. It's not and add them and multiply them and take inverses, staying within this format. And they will then be, if you multiply them, be a little bit wider, and then you compress. But you never go back into the full setting. So therefore, it is important that you have an algebra that works in this thing, and that's what we are using in this setup here. Now, afterwards, so we did this further, and then a little bit later realized that you can cheat a little bit more. So in order to, here you produce the half-space Green's function, which then was compressed by taking all of these points here and eliminate them as in a Gaussian elimination. Why not just put an absorbing boundary condition nearby here? So you have the absorbing boundary condition or PML layer following the sweep here. And this is a pretty good approximation of the other ones. You could do that. So this also works. There are differences in this. This is harder to do because you have to do this algebra and you have to do this compression structure over there. But once you've done it, you have a much better setting. You have fewer iterations, and you can, even if you go a little bit further in accuracy, have it as a direct solver, sort of, which has become popular if you have redo it a lot of time. You get an LU decomposition. If you do this way, it is a shorter construction time because you don't have to do this algebra. And the most important part is it allows for more general grids. You could do an unstructured grid. The other one, you have to have the geometry following the algebraic structure. So a row should be a line or something close to that and doing that. On the other hand, it's not as good because you didn't do the full elimination, which you would like to do. And it is pretty accurate close by, but if you have diving waves going on, that is not. And therefore, you have more iterations. And actually, you need to have a little bit complexity in your coefficient in the Helmholtz equation. So at far distance, you can eliminate that where you really have the dispersion error. But practically, this engineering thing, it works a way in doing this thing. And practically, it looks like linear. So you could run a waveguide in 3D, and you would see, like I say, that the number of iterations, which otherwise goes up algebraically, with n stays in pretty close to each other, depending on the setup doing that. The time cost also scales very linearly with the number of unknowns, or depending on the wavelength. It depends, of course, on the dimension. This was a 3D case. You could do that, a similar approach for the Maxwell's equation. So here is a circular radial domain in this case, with a finite element type of discretization, Nedlec elements. And then you could look at the conducting case, or you could do a cloaking form or whatever. And again, the number of iterations stay, which doesn't do with standard, the ILU, etc., very similar, and also the setup time and the solve time scales with the number of unknowns here. This end reasonably linearly in the practical case. We were driven a little bit, being in Texas, by applications to seismology. We will come back to next week in a more analytic setting, where you have a large domain, and this is the waves coming out. This would be the geometry, and that shows that you, even if, I should say that the theorem here in this case was also for constant coefficient. You could do a perturbation around that, but serious variable coefficient, that's harder. But even with constant coefficients, you can get, even with variable where you have salt, which is a rather strong heterogeneity, you can do a good job. And again, get scaling that is almost constant in the number of iteration, and the time very much aligned with the number of total number of points that are involved in the setup, and compares well with the accuracy with the test cases that they have. We did it in a rather large-scale simulation where you're talking about thousands of processors, and it still scales well. So there was one of the students of Lessing that did this and rewrote, so to speak, the Leipzig structure of architecture for doing this, working on thin SVDs all the time, the algebra in distributed computing way. So the final part here, I don't know why it is slow to react, will be, now we did this decomposition here between two domains, and we said that you can't use the way that people do it for elliptic problems, and we need to do that. The question is, do we actually need to do this? So we try to look at some lower rank bounds in this case. It's a little bit harder, of course, to say that there's no way you can do this in a certain setting, then have an example and then prove that it's possible. So for the low rank estimate, I don't know what's going on here. So the idea is here to look again at the Green's function. So if we think about the discretized Green's function here first, so you have the x direction, which is one of these groups of particles. You would like to do the interaction in a compressed way between those. So this is the x direction. Then we pick two different points in y. So this matrix, you're interested in asking whether this matrix, which has discretization along x, discretization along y, whether it is compressible. A certain case where it's not compressible is, of course, where these guys are orthogonal in this way. Then you have full rank in this case. So let's see how close to not being. How close are these? How you look at the angle between these two, or you could say, how do they decorrelate when they become further apart? We can do that. So that would be a question. And then the next thing is, if they decorrelate a lot, if we are close to that, what does it say about ranks? These two steps. So let's take the first step over there. So then you can get a theorem out of that, where you can see that this product, and the tildes here mean normalized Green's function. So this would be expression. Here you have the 3D Green's function, and here you have the normalization. That you can actually bound this. This is small. It's close to being orthogonal in a way here when these comes further apart in this case. And these are oscillatory ones. So it's easy to think that they would decorrelate, that they would, when you multiply, take the inner product between them, that would be small. And that can be expressed then in terms of the dimensions of the sets. So D here is the dimension of the sets. It could be that there are sets in 3D, but it could also be that it's a surface in 3D, as we have with the integral equation case. So this is what is done. And proving this is a number of cases. So you have to pick the points y, and then you have the domain x, where you integrate along in the x direction, the long direction x here. You integrate over the domain of x. And then you look at different cases when the y points are outside, when the y points are inside, 1 point is inside. So it's a little bit tedious thing. And where you get a true contribution and they don't cancel out is depending on stationary phase setting. So it's fairly straightforward, but because of the number of cases and it touches in an infinite number of points, blah, blah, so you have to approximate these things here. So the idea is, for example, if you look at the case which we have over here, then if you redefine it, you're having to look at the classical problem for stationary phase, where this is a modified phase function in doing that. There, if you have the setup over here, there is no stationary point, so you can integrate by parts once and you get out the k term, and then you can use stationary phase argument on the boundary integral, which actually comes in there. So this approach, you have to go through all these cases, and it turns out you get this estimate in the end. That is what's doing that. Now you have this thing. So this is an estimate. If you know that it decorrelates in the following way, or you get the angles depending on this difference is of the way that you have this part, and you want this kind of approximation, a separated approximation. So this is one constraint that you're given by the earlier estimate, and this is what you would like to do. Then it depends that the rank here must be larger than these types of values that were given here. And that tells a little bit about how it looks like. So that's the analysis behind these things. And to do this, then we base it on a discrete lemma. So these were integrals over the domain of x. So what we do is we discretize the problems with two discretization. You have a fixed number of y points, and then you discretize x, so you do a Riemann sum instead of the integrals, and then you estimate the difference between that. So you have then a matrix that is built up by these inner products in this case, where they depend, the y values depend, sits in y. So it is a problem of approximating a set of almost orthogonal vector by a linear space here. And that's a little bit like the Johnson-Lindenstrauss lemma thing. And there is one proof here where Noga did, where he, to prove that that was sharp. Of course, he didn't prove the lemma, that was done before, but to prove a sharp estimate, where he looked at the matrices over here that were almost orthogonal with small values on the side, and then what rank comes out of that, depending on epsilon. So that is where this possibility is. So if we modify this a little bit, this kind of proof, the difficulty is that you have to replace this thing, because this would be depending on the decorrelation that it is, and that depends on the difference between these two. When they are close together, it is quite correlated and further away. So instead of summing over all the b values, we sum over shells of larger differences between these things, and then essentially use the other way, the way that Noga did in this, in order to get the rank estimates that we had in the end. And if you do that and take a fixed domain with order 1 and let omega be different, then you could see that this n doesn't scale with k, the rank in this case, better than k squared. So if you would have that, and instead of what we had before, we had a domain and omega becomes large, this guy has to be sent to infinity at a certain range. Or, yeah, it depends on the scaling, or this has to be small compared to the other one. That is what it is. So in this case, you could see that you cannot just take fixed domains and then let k be very, very large and still have a low number of in the separable approximation setting over there. Okay, so we could look at cases where you have all in 3D, but you have subsets, like when you do integral equation. You could take lines that are aligned like this. You can take planar sets that looks like that. You can take planar sets that look like that. And then you can go back into the first decorrelation part and look at the estimates that comes in there. You find that here you have a finite number of points independently of k, which is the one we used in the second theorem in this case. So that's sharp. And if they lie like this, then they grow with k, which is k is number of, you could say frequency in this case. And if they are that, they're even worse. The frequency goes up at a higher rate than the other guys. So this you could see here, if you have these two lines there, then it was, and there is no boundary whatsoever. It's an open boundary. And that's the case we had when we assumed an open boundary in this case, or an open boundary condition. Then you get a separable approximation to arbitrary accuracy with a finite number of terms. The number of terms grow with the log of the error estimate in this case. But if you put a Dirichlet or Neumann boundary condition here, then of course via the reflection you have this guy interacting with that guy, and then you get the order k thing. And that's why in the case with the reflection there you have a much higher rank, much higher, larger number of singular values in this case than you have in the other one. So that sort of tells the story that this is a way to do it in many ways, and it's not completely one-to-one. It's not sharp in all cases. It is in this case, but otherwise it is not. But at least it tells you how to look at these problems. And when it comes to the lower bounds in this setting, it's the only results that is around. So this was it. The idea here would be that linear scaling is possible for the Helmholtz type of problems. Linear, being quotation mark, can only prove that in constant coefficient setting or small perturbations around that. And also we also need an open boundary, for example. In the other case, one can put that together in a domain decomposition setting, probably, but that's we have not done in the setting over there. And they were separated in two cases. One we used fast multipole method for integral equations, and the other when we use a preconditioning setting for differential equations, variable coefficients in these cases. So there, and the interesting, one thing that is interesting is that you have to use sort of the analysis part quite far and know what to do, and then you can switch to the more sort of data intensive doing fast SVDs in a randomized way in order to combine them and get an efficient overall work. So I think this interaction is quite, and people, some of the oil business thing have implemented these guys and are running that over there. Lower bounds are possible. There it's a paper that it's with Hongkai Zhao that I wrote over there, and it's coming out in the communication of pure and applied mathematics sometime this year. So we did it a little bit earlier, but then we were sitting on it and not doing it. So it's, but anyway, so it's that is not published yet, these results, but it's been on the archive. And that's it. We'll stop for that. Thank you. Now.